When a subway train enters a tunnel, it does not move through empty space. It pushes a wall of air ahead of it and pulls another behind. Most days, that moving train helps the tunnel breathe. During a fire, the same airflow can carry smoke toward the people trying to escape. This is why the enormous fans hidden beside stations and beneath ventilation shafts are not simply underground air conditioning. They belong to a system for controlling where air goes. Start with the train. In a narrow tunnel, there is little room for air to pass around the cars. The train behaves like a loose piston. Pressure rises in front, falls behind, and air moves through stations, side passages, relief shafts, and every opening connected to the surface. Transport for London says this piston effect provides most routine ventilation on the underground, supplemented by shafts and fans, especially on the deep tube lines. Other railways use different designs, but the mechanism is the same. The train itself becomes part of the airflow network. That moving air helps exchange stale tunnel air with outside air. It can also create the blast you feel before a train appears, but airflow alone is not cooling. Underground railways accumulate heat from propulsion, braking, train air conditioning condensers, lights, equipment, passengers, and the surrounding structure. Singapore's downtown line, for example, uses under-platform exhaust fans to remove heat released when trains stop, while Transport for London describes station and mid-tunnel fans that force air into or out of deep tunnels. So normal ventilation is already a balancing act. Use train movement where it helps, relieve pressure where it does not, and mechanically move heat toward a place where it can leave the system. Then a fire starts, and the objective changes completely. Comfort no longer comes first. The system must protect a route through an environment where smoke can remove visibility, carry heat and toxic gases, and make the obvious exit impossible. At that moment, the tunnel stops behaving like a simple tube. It becomes a controlled air circuit. A modern tunnel ventilation system is not one fan at one opening. It is a network. Large fans connect the tunnels to shafts. Dampers open one route and close another. Booster fans help where crossovers or sidings complicate the path. Under-platform exhaust can serve both routine heat removal and emergency smoke extraction. Sensors, communications, control software, electrical power, and operators decide how those pieces act together. Many tunnel fans are reversible. In one direction, they supply outside air. In the other, they pull tunnel air and smoke toward a shaft. Dampers are the routing switches. The same fan room may be connected to one running tunnel, the other, or a selected section. During a fire, operators can place fans on opposite sides of the incident into a push-pull arrangement, fresh air from one side, exhaust on the other, to move smoke away from the chosen evacuation route. But there is no universal button marked Remove Smoke. Federal Transit Administration research describes cases where driving smoke in one direction may be useful when passengers are all on one side of a fire. If people are on both sides, preserving a smoke layer with very low longitudinal airspeed may be safer than mixing smoke through the full tunnel. Tunnel grade, train location, congestion, fire location, and the direction people will evacuate all change the answer. Even another moving train can overpower the planned airflow, which is why an emergency strategy may stop other trains, remove traction power, verify where passengers are, and only then select a ventilation mode. The 2015 Elephant Plaza smoke accident in Washington shows why sequence matters. According to the National Transportation Safety Board, an occupied train stopped in heavy smoke beyond the station. Under-platform fans at Elephant Plaza were placed in exhaust before ventilation shaft fans near the smoke origin were activated, and the train became enveloped in smoke. That does not mean exhaust mode is inherently wrong. It means that airflow has consequences, and the useful direction depends on the whole incident. A fan command is therefore also an evacuation decision. It determines which side receives fresh air, which side receives smoke, and whether the path shown to passengers agrees with the path the ventilation system is creating. The real product of these giant machines is not moving air. It is a few minutes of visibility and breathable conditions along the one route people need. The word giant is not an exaggeration. Singapore's Land Transport Authority describes tunnel ventilation fans at least 1.6 meters in diameter on the downtown line. In New York, an existing fan plant considered for the 2nd Avenue subway was rated at 600,000 cubic feet per minute, about 283 cubic meters every second. Those are examples, not universal specifications, but they reveal the scale of the task. A tunnel contains an enormous volume of air, and the fan is not moving that air across an open room. It must drive it through a long, narrow path with friction, bends, shafts, grills, dampers, trains, and pressure changes. Every obstruction adds resistance. The harder the path resists, the more pressure the fan must create to deliver useful flow at the fire. This is why capacity on a nameplate is not the same as airflow at the incident. The system is designed as a pressure path. Engineers simulate specific tunnel sections, train positions, temperatures, and smoke movement. They test fan and damper performance, measure tunnel airflow, and commission the pieces together. Equipment may also have to keep operating in extraordinary heat. On Singapore's downtown line, the ventilation equipment described by the authority is rated for 250 degrees Celsius for at least 2 hours, with redundant fans so the design can still function if one fan is unavailable. Emergency power matters for the same reason. A smoke control system that disappears with the normal electrical supply is not a complete emergency system. Federal guidance therefore treats alternative power, remote controls, local controls, alarms, procedures, and trained staff as part of ventilation, not accessories to it. Modern control systems can hold pre-programmed scenarios for known tunnel sections. Detection and signaling identify a possible incident. The system recommends a configuration. An operator verifies the situation, chooses or changes the mode, and watches whether the commanded airflow actually appears. That final distinction is crucial. Command is not proof. A damper may not reach its position. A fan may fail to start. A smoke source may be somewhere other than first reported. Passengers may be on both sides. The system must reveal those mismatches quickly enough for the strategy to change. So the largest object in the fan room is only one part of the machine. The complete machine stretches from a smoke detector, through the control room and power supply, into fan blades and dampers, along the tunnel, and finally to the evacuation walkway. Its true size is measured not by the fan diameter, but by how much of the railway must agree about where the air should go. A subway tunnel does not need giant ventilation machines because underground air is mysterious. It needs them because air has mass, tunnels resist its movement, trains disturb it, fires heat it, and passengers may have only one safe direction to walk. Most days, trains and shafts make the system breathe almost invisibly. On the worst day, reversible fans, dampers, power, controls, and people must turn that breathing into a deliberate path. The fan is the part you can photograph. The infrastructure is the agreement behind it, where the fire is, where the passengers are, which route stays tenable, and where every cubic meter of smoke should go instead. That is what sits behind the grill on a subway platform. If you want to see another hidden system beneath an ordinary journey, subscribe to Beneath the Network, and tell us which machine we should open next.